All right, let's begin. All right, great. Well, I hope by Thursday, the Boston Red Sox will have won the World Series. So, what's on the menu for today? All right. First of all, I'm going to look at several examples on the method of undetermined coefficients. For those of you who haven't picked up set homework number 6, please do so before you leave today. It has several questions on it, 7 or 8, and I'm guaranteeing you that your quiz, not tomorrow you've no quiz, but the quiz on November the 6th, the following Wednesday, tomorrow week, will contain one of these examples. So what you'll have to do is be able to do the whole set, because randomly the different examples will be handed out for the quiz. So you can be absolutely prepared. It's very important that you know this method of undetermined coefficients very well, because it is the method that you will mostly use for most applications that you come across in solving second and even higher order linear equations with given right-hand sides. Now, let me remind you what are the rules. The equation has to be on the form this, or it could be higher order, but as long as the coefficients are constant, here P and Q, constants, and the right-hand side has to be combinations of functions which have the form, each of which has the form t to a non-negative integer power. 1 over t doesn't work. Log t doesn't work. So t to a power, non-negative integer power, m, e to the at, and either cos bt or sin bt. Now, some very clever people have asked some good questions. My TAs passed on to me this morning, and it's a very good question. They said, why this method that you've used, that you form an auxiliary set in order to obtain the particular solution? Remember, the general solution is the sum of any particular solution plus the general solution of the homogeneous equation. And we have a rule whereby we go about preparing the special or the particular solution. We form an auxiliary set from the functions we're given on the right-hand side. Then we either modify it or not modify it, depending upon whether they match solutions of the homogeneous equation. So the question is, why does this sort of thing, why does it work? Well, the answer is that for functions of this sort on the right-hand side, essentially, on the left-hand side, if I take y, if I look for solutions y, which are linear combinations of all the functions that I get by repeatedly differentiating these things here, then I have to be able to match, because I have a finite number of terms on this side. We know that there's just a finite set of linearly independent functions which you generate by repeatedly differentiating that. So then on this side, since this is just y, this is just the derivative, this is just the second derivative, these are all constants, I can only generate the terms that are over here. And therefore, by the linear independence of this set in which I expand the particular solution, I can match the various functions, the coefficients of the various functions up. And therefore will always obtain a solution. I won't obtain a solution, for instance, if this guy is not of this form, like if it's like I say 1 over t or log t, because when you differentiate that repeatedly, you go on forever. 1 over t minus 1 over t squared, 2 over t cubed, etc., etc. So the right-hand side has to be in this form. The method we'll start on Thursday is much more powerful, method of variation of parameters. It works even when these are not constant and these guys are just general functions of t with a certain smoothness, in other words, a continuous or something like that. The method of variation of parameters, you might say, well, why didn't we just learn that and use that all the time? The problem is, as you'll see when we do it, it's powerful, but it takes a lot of calculational work. And very often, for the rather simple examples that you come across in practice in your various subjects, like mechanics or chemistry or optics, it takes forever working through the method of variation of parameters. Now, if you work through that method and do it correctly, you'll have no trouble. You will get the answer. But we learn a lot by being able to do the answer much more quickly using the method of undetermined coefficients when the equation has this particular form. So second on the menu today, I'm going to do some examples of this kind, and then second on the menu, I'm going to go over what the solution to this second order equation with constant coefficients and a periodic forcing in terms of the cosine omega t, what does the solution tell us? And in this today, I'm going to use as my working example the mass spring problem rather than the LRC circuit. But you'll see complete matchup of the various ideas. This will also address question number 4, I believe, of the trial exam number 2. Trial exam number 2 is actually already in your lecture notes 16 through 21. Pages 22 to 28 contains trial exam number 2 plus a mock exam. The trial exam will take you quite a long time to do. The mock exam is a good exercise for seeing that you can get things done in an hour and a quarter. You know, the length, it's typical of the length of the exam that you'll actually meet on November the 21st. So start working on that trial exam number 2 now, and one of the questions on it we'll be more or less addressing today. Right. Final reminder. If you haven't been to one of the tutor sessions and signed up, or my session last week, Wednesday or Thursday, and signed up, you have one last chance to get credit for your quiz number 8. And that's tomorrow at my class there. Yes?
Do the TA office hours count?
No. I made that clear. TA, the whole inducement is to get you going both to my class and especially to the tutors. I mean, we've set up this tutor scheme for you guys. I want you to use it.
Is there a required run time with the state? Like if we have a class at 8?
It's quite okay. If you come at 7:15 and stay till 7:45, I will give you full credit. Good, but bring good questions. I'll be looking for you. Right. So, this is the guy we're going to look at first. This has the form of the equation up on the right-hand side of the upper board. It is d2y by dt squared plus y equals t sine t. Y of naught is 1. dy by dt of naught is 0. All right. We now are going to go through our various steps. Step 1. In fact, let me just move this up the board so I have a bit more room. So d2y by dt squared plus y equals t sine t. Y of naught is 1. dy by dt of naught is 0. Okay, step 1. What is step 1? We identify the solutions of the homogeneous equation. This equals 0. All right? I want you to find the solutions of d2y by dt squared plus y equals 0. Okay, any answers? All right, e to the it and e to the minus it, but I want real solutions. So cosine t and sine t, right? The combinations e to the it plus e to the minus it over 2 is cosine, and e to the it minus e to the minus it over 2I is real, and it's the sine. So the solutions are cos t and sine t. Step 2. We want the auxiliary set of t sine t. Okay, so you take this function and you repeatedly differentiate it and until you run out of new functions. So please do that and tell me what you get. Right, so t sine t, if I differentiate it, I'll get what? T cos t plus sine t. So there I must have a t cos t in here, and I must have a sine t. Now differentiate again. What am I going to get? Well, when I differentiate this, I will get a, when I differentiate with respect to t, I'll certainly get a cos t, as I will when I differentiate that, and so on. So cos t has to be in the set. Any other things? No, because any differential of any combination of these just gives you back combinations of these. Okay? Any differential, no matter how many times you derive that, take derivatives, you end up with linear combinations of those four functions. And they're all linearly independent on the interval minus infinity to infinity. Okay, step 3. Is it necessary to modify? Are any of these solutions of the homogeneous equation? Yes. And what's the rule? We modify by multiplying this set, each member of it, by the lowest power of t, so that the remaining, what we get when we do that, no longer satisfy the homogeneous equation. So we'll get then t squared cos t, t squared sine t, t cos t, and t sine t. Okay. Step 3, or step 4 rather. We seek our solution as a linear combination of these. So it'll be a1 t squared plus a2t times cos t. That's a linear combination of this and this, plus a3t squared plus a4t sine t. Question?
What would happen if you multiplied by t squared instead? What would happen if it was the lowest power of t?
Right, very good question. All right, if you multiply by too many t's, so that this would be t squared, you would find that you would generate a term which was the terms which would be t times sine t and t times cos t would have trouble. It wouldn't be too bad if you if you made this t cubed cos t, t cubed sine t, t squared cos t squared t. As long as you include the t cos t and t sine t, automatically the higher order ones won't appear. So, very good. So now we seek solutions in this form. What you do then is you substitute yp double prime plus yp plus y p equals t sine t, and you match coefficients of t cos t, t sine t, t squared cos t, t squared sine t, t cos t, and t sine t. This will give you 4 equations for A1, A2, A3, and A4. And the answer you'll find is YP. YP is a quarter, mine is a quarter t squared cos t plus a quarter t sine t. So what you're going to find is the A1 will turn out to be minus a quarter. The A4 will turn out to be equal to minus A1, which is plus a quarter. The A2 will be 0, and the A3 will be 0. Now, you have to go through the calculation. You have to differentiate this once, then twice, then substitute it into the equation, and then match coefficients. Now, on the second example, I'll actually go through the calculations. But for this, I want you to go through it on your own, and if you have trouble, bring it up with your TA in your recitation class tomorrow, or in his office hours. The general solution then is A cos t plus B sine t, and then with the particular solution minus a quarter t squared cos t plus a quarter t sine t. You use the 2 initial conditions to find A and B. And what you'll find, I believe, is A turns out to be 1 and B turns out to be 0. Yep. Okay. Let's try another example. Okay. So, d2y by dt squared minus y equals e to the t plus t. y of naught is 2. dy by dt at 0 is minus a half. Okay. Step 1. Identify the solutions of the homogeneous equation. Question, yes?
Yeah, I was going to discuss step 1 of the last one. How do you get y? Like, when you substitute in for y and
Yeah.
squared y reduces.
Right. This was the auxiliary set of the right-hand side. I had to multiply each term by t in order to essentially move these up, because these satisfy the homogeneous equation. So then the basis in which the solution is going to be given will be a linear combination of those 4 functions. Okay? So it's a1 times t squared cos t plus a2 times t cos t plus a3 times t squared sine t plus a4 times t sine t. And I just couple them in this way. Okay? So this expression is simply a linear combination of those 4 functions.
Can you just raise the bar up a little bit?
Yes. Yeah. Right. Question.
Why in the modification is it not just t squared? Like, I don't understand why t cosine and t sine, considering they're the derivative set.
Right. We have to the rule is we have to multiply every term here across by the lowest power, integer power of t. So,
That's why I'm confused. Because
yeah.
I'm confused why we don't just have, for the modification, just t squared cosine t and t squared sine t.
And then leave sine t and cos t here? Is that what?
No, I understand why we don't have cosine t and sine t.
Right.
But I don't understand why we have t cosine t and t sine t.
Because when I multiply this set across by the lowest power of t, in order to,
It doesn't.
I have to hit everybody across in the auxiliary set. The reason is, if I look for solutions in the form, if I added these, a5 sine t plus a6 cos t, I automatically get 0, because d2 y by dt squared plus y of both cos t and sine t automatically are 0. Question.
Sorry, just on this step again. So is the rule more that you multiply by the lowest power of t found in the auxiliary set, or is it that you multiply by the lowest power of t such that none of the...
You just multiply by the lowest power of t such that none of the when you do that, none of these terms satisfy the homogeneous equation. Which one?
The t sine t.
No. No, it does. This does not satisfy the homogeneous equation. It's only sine t and cos t satisfy that. Actually, let me give you a very simple example. I'm glad you're raising these questions. How about d2y by dt squared equals t? Right? Let's try and solve this. Step 1. What are the solutions to the homogeneous equation? Well, 1 and t, a plus bt. Okay? If I solve d2y by dt squared equals 0. Okay? Then the auxiliary set of t, the right-hand side, is t and 1. Right? Because when I differentiate this repeatedly, I'll only end up with combinations of t and 1. In fact, I only end up with t and 1. Now, I have to modify this because these guys satisfy the homogeneous equation. So, let's modify once. T squared t. Do any of these satisfy the homogeneous equation? Yes, we're still in trouble. So we have to modify again. So t cubed and t squared. So then we look for a solution in the form yp equals a1t cubed plus a2t squared. Okay? And the general solution will be a1t cubed plus a2t squared plus at plus b, because that's the solution of the homogeneous equation. Now you can see that if I just integrate this directly, I am going to go up to t cubed, because integrate it once, dy by dt equals t squared over 2 plus b. Integrate again, y is t cubed over 3 plus bt plus a. So what you're going to find, if you substitute this in the equation, the a1 will be a third and the a2 will be 0. So you can see why it is that you have to multiply the members of the auxiliary set, because essentially you're sort of resonating with the right-hand side is forcing the left-hand side very strongly. Okay, let's go back and start doing this example now. These are good questions. Step 1. What are the solutions of the homogeneous equation? Yes?
E to the t and e to the negative.
Yes, e to the t and e to the negative t. Now, step 2. Now, I've told you before that you can do this problem in 2 stages, if you like. You can do the problem by solving with the right-hand side e to the t, and then do it again with the right-hand side t. But I'm going to choose to do them all together. But there's one important thing I want to bring your attention to when we do them together. So I have to write down the auxiliary sets for each separately. So what's the auxiliary set for e to the t? E to the t. You get nothing more than e to the t. What's the auxiliary set for t? T and 1. Now, step 3. Do I have to modify this e to the t? Yes. Do I have to modify this? Are either of those solutions of the homogeneous equation? No. So it's t and 1. So no modify here. And you have to modify here. Okay? So you only, when you multiply across by t, you only multiply that set of functions generated by the functions separately. Now we can seek a solution. We seek a solution in the form yp is a1 t e to the t plus a2 t plus a3. This gives me yp prime. This will be a1 times t plus 1 e to the t when I differentiate this. Then plus a2. Yp double prime will be a1 times t plus 2 e to the t plus 0. Now I substitute this into the equation. And what will I get? Y double prime. So I get a1 times t plus 2 e to the t, minus y, minus a1t e to the t, minus a2t, minus a3, and that's got to be equal to e to the t plus t. Now, as always happens, when you have to modify, you get a natural cancellation, so you end up with the right number of equations for unknowns. In other words, the te to the t terms cancel. Now, the coefficient then across of e to the t, I have 2a1 on the left-hand side and 1 on the right-hand side, so a1 is a half. The coefficients of t, I have minus a2 on the left-hand side and 1 on the right-hand side. So a2 is minus 1. Sorry?
What about A3?
What about A3? A3 is t to the 0, multiplies 1, so I get minus A3 equals 0. So then my solution is y general will be the solution of the homogeneous equation, ae to the t plus be to the minus t, and then I have plus a half te to the t minus t. And if you look at the initial conditions will give you that A and B are both 1. Okay. So, what you must do now is lots and lots of examples. On page 5 of lecture notes 16 through 21, you will find several examples listed, and then actually most of them are carried out. In the set homework that I've handed out today, there are 7 problems, and if you can do all of those, you'll have no troubles with this method. Okay? So you must try and do all these examples. Good. So now I'm going to go to this problem here. Right? We're now going to talk about, we're going to first of all find the general solution of this equation. We've already done it last day using the letters L, R, C instead of the letters M, B, and K. And we'd have V0 cos omega t on the right-hand side. Today we've F0. So I'm going to use the solution from last day, and the main purpose of our discussing this is to interpret, understand what the solution is telling us. Okay, and write it in various useful ways. So, the general solution of this equation, x, is the solution of the homogeneous equation, which has the form a e to the minus b over 2mt cosine root k over m minus b squared over 4m squared times t plus be to the minus b over 2mt t sine of this same expression, k over m minus b squared over 4m squared times t, plus f0 over omega, and then this term, this impedance, z of omega, times cos omega t minus phi, where it turns out that z of omega is the square root of, it was 1 over omega c minus omega L last time. Now it's k over omega minus m omega all squared plus b squared. The cosine phi is the reactance, which in this case is k over omega minus m omega divided by z of omega. And the sine of phi is the resistance divided by z of omega. So this is what you get as the particular solution if you just follow the steps we did in last day's lecture. Okay, it's also done out very clearly in the notes. This is the solution of the homogeneous equation when we assume that the spring force k over m, that this guy is much bigger than the damping b squared over 4m squared. So this guy is positive, so we get solutions. The roots of the characteristic equation will be complex conjugates. And so we get some damping, a cosine, and a sine, like that. We call this part of the solution, is sometimes given the notation x of c of t. C stands for complementary function. I don't know what the origin of the use of the word complementary function was, really. I suppose it complements the term that survives in time, the term that doesn't get damped. This guy is often denoted as xp of t. So the general solution consists of two parts. One part is the solution of the homogeneous equation. The other part is the non-decaying part, the non-decaying response to the sinusoidal or the forcing on the right-hand side cos omega t. Okay, so those two solutions are sort of illustrated well here in this example that I handed out last day. This is a situation where you see the complementary function with the free constants a and b is there so that you can satisfy the initial conditions on x of 0, the initial displacement of the spring, and the initial velocity of the spring. In question number 4, we pull the pan down 4 centimeters, and we have to use always consistent units, so that's 1 over 25 in meters. We pull it down here, and we let it go from rest. So v of 0 would be 0, and x of 0 would be 1 over 25 in meters in this particular question. So knowing the initial conditions, you can determine a and b. And why this is important is it allows you, this guy on its own does not satisfy the initial conditions. So what happens? You start off and the thing is satisfying the initial conditions, okay, and then it oscillates. But when it's oscillating originally, the damping term here, t is quite small, the b over 2mt is quite small, so it looks as if you have oscillations with this particular frequency and the frequency omega. And what I'm going to show you, probably at the beginning of next day, look at the way, since these two frequencies are quite close to each other, in this example, you get a lovely beating. You see, you get a modulation signal. Okay? In other words, you get wiggles under this envelope. It's like a little wave packet. Are many of you surfers? Who has surfed? I'm not going to ask you a question. You don't have to... This is not a trick to find somebody to answer questions. You've surfed, right? And you see waves tend to come in packets. I mean, you get a big wave and then maybe a much smaller one and so on, and then you wait for the next big wave. Is that true? So very often you see waves arriving in packets. And so this is at the initial stages, when the damping of the complementary part here, when this guy is fairly small, in other words, t is fairly small, so this e to the minus b over 2mt is more or less 1, then this guy and these guys kind of beat together. Sometimes they reinforce, as when the amplitude of the motion gets quite big, and sometimes they cancel. You know, if they're slightly different frequencies, sometimes they'll be matching, and then the two oscillators, sometimes they'll be out of phase, and then you get damping. Then you get cancellation. So this phenomenon beating, this is how you modulate signals. Okay, this is this amplitude modulation I talked about last day. But eventually, in this case, after how many units? About, I think I took t equals 40, so after about 20 units here, the initial conditions, now this guy has died away. In other words, this guy would be something like maybe b over 2m times t is about 4. Okay, and e to the minus 4 is quite small. It's like 1 over 80 or something. Okay, so then the solution gets dominated by the surviving part. Okay, the steady state, the oscillating surviving part, which isn't damped, and there you see it. There, it's this part here of the solution. You see, now you only have this one frequency. Okay? Now, I'm going to show you, we're going to discuss these two solutions separately. The first part of the discussion is essentially a repeat of the discussion we had last day in the context of the LRC circuit. The second part of the discussion is I'm going to show you how to rewrite both of these terms in our favorite form, a squared plus b squared the square root cos omega t minus phi sort of stuff. Okay, but first let's look at xp. And we'll do that on this blackboard here, or whiteboard here. Okay. Okay, so the surviving, the asymptotic or the long time surviving part, xp of t, this is the displacement now. This is f0 over omega of z of omega times cos omega t minus phi, where the z of omega is given by this expression and the cos and the sine are given by these expressions. So we like actually to record the solution in terms not only of the position of the displacement itself, but also the velocity. And if I differentiate this with respect to t, I'm going to get this to be minus f0 over z of omega sine of omega t minus phi. Now I choose to always write things in cosine form, so this is f naught over z of omega times cosine of omega t minus phi plus pi by 2. Okay? Why? Because minus sine of this argument is equal to sine of phi minus omega t, and sine of phi minus omega t is cosine of pi over 2 minus phi minus omega t, which is this. Okay. Now, when is z of omega, let me write down what z of omega is again here. It's the square root of k over omega minus m omega all squared plus b squared. The cos phi is k over omega minus m omega over z of omega. The sine of phi is b over z of omega. Notice that cos squared plus sine squared is 1. So there always is an angle phi between minus pi and pi, which satisfies this and this. Okay. At which value of omega am I going to get the strongest response? So at which value of omega, well, the strongest response, the only thing that I can change here, is the z of omega, this impedance. At what value of omega is the impedance the smallest? So that 1 over the impedance is the biggest. So if I make this small, I make 1 over z big. So what value of omega should I choose? Yes. Yes. So we're on resonance. In other words, 1 over z of omega is maximum when omega is the square root of k over m. Okay? In that case, what is 1 over z of omega? What's it going to be equal to? 1 over b. What's phi going to be equal to on resonance? If I choose omega to be the square root of k over m, oh, you've made this 0. So what's cos phi going to be? If I choose omega so that omega is root k over m, what's this equal to? 0. Okay, what's z of omega equal to again? Z of omega is b. So cos phi is 0, sine phi is 1. So what's phi? Pi by 2. So on resonance, the velocity is simply f0 over b times cos omega t. In other words, when you match the frequency here, see the frequency on the right-hand side, What's the natural frequency of the oscillator on the left-hand side? If we take the right-hand side to be 0, and supposing we leave out the damping, B, then we have m d2x by dt squared plus kx equals 0, or d2x by dt squared plus k over m x equals 0. The solutions will be cos root k over mt and sine root k over mt. So root k over m is simply the natural frequency of the undamped oscillator. Omega is the forcing frequency. When the forcing frequency is equal to the frequency of the undamped oscillator, I'll come to your question in a minute, then we get the largest response in the system. And in fact, when you're at that position, look what happens. The md2x by dt squared term and the kx term exactly cancel. Right? Because they exactly cancel, because this term and the k over m, because the omega, you see, is simply root k over m. So that term cancels the restoring force. And then the damping matches the forcing. And that's what this says. Vp, which is dx by dt, Vp of t, which is dxp by dt. Okay, this is the surviving, the continuing part of the solution is just gotten by matching the damping term with the forcing term. So, in a sense, you take out the oscillator altogether. In fact, you get Ohm's law even though the voltage is actually time dependent. Okay, in this case, the damping matches the force acting on the spring. Now, why is this important in practice? If you take many structures, like a bridge, or even people, they are often modeled by interconnected sets of springs. Okay, like a bridge essentially is like the combination of lots of independent springs. And there's sort of different motions. You can have a motion of the bridge that the whole thing sways backwards and forwards like that. The bridge would be like this, and it would sway backwards and forwards, say, towards me and away from me. Then you can have a mode of the bridge in which it sort of buckles once and then moves backwards and forwards like that. Okay? It's like a violin string. You can have the fundamental mode, which is just the bridge going backwards and forwards like this, and then the first octave, the next mode, and so on. So you can consider many mechanical structures, and often in crash worthiness tests, they model us as combinations of sets of springs, and then they're acted upon by certain forces. In the bridge example, the forces that will act on it are forces supplied by wind, usually. And if the wind just blows straight, no matter how hard it blows, generally, bridges are built to survive such wind quite high wind velocities. What they may get into trouble with is if the wind is fluctuating, if there's a lot of turbulence, if the wind is fluctuating and has lots of frequencies. So the actual force is an oscillatory force, like F0 cos omega t. Now, if the bridge's natural frequencies for whatever mode, this mode or the mode with one buckle or two buckles in it, if any of those frequencies happen to match the frequency contained in the pressure variations in the air, the wind, then the bridge will respond rather dramatically. Because the damping that you can put in these bridges isn't very great. I mean, you could see that. For instance, like take a bus stop. Okay, a bus stop, okay, you give it a push. It takes, you know, it wiggles quite a few times before it comes back to rest. So if you want to knock down a bus stop, one of its modes is this mode. Okay, it goes whing, whing, like that. The other modes are harder to excite. I mean, the mode that goes like whing, whing, like that, you give it a press, okay, once. If you keep hitting it in tune with its natural frequency, backwards and forwards, very soon these oscillations will build up until you reach some stress breaking point, and the bus stop will shatter. Likewise, bridges come down that way. Bridges start oscillating, and if there's not enough damping, as is often the case, then you can have real troubles. You can bring a bridge down, and this has happened in many cases. In a minute. What they do then, what engineers will do, of course, is they will determine if it's likely that any of the natural oscillation frequencies involved in this big structure of the bridge are likely to be contained in air pressure fluctuations. And if they are, then they will put braces or struts they will put them in such a way that effectively they raise the damping to make sure that that particular mode is heavily damped, so the response won't be too great. Okay? So now we had two questions, one here and then one here. Yes?
My question is, what, you know, there's all these examples of the LRC and the Jones swing. So, and I guess they all share this thing. What is, you kind of answered it, but what are physical representations of omega and z of omega? Okay. Yeah, omega is, let's talk about what the omega is. First of all, let me introduce the notion of a periodic function. Periodic function. Okay. Let capital T be the smallest value of t for which x of t plus capital T is equal to little x of t for all little t. Okay, then we say that the function x of t is periodic with period t. Right. In this case, x of p of t, what is the smallest value of t? Let's start at t equals 0. Let's march forward in time. When will the xp at 0, at what time will the xp at that time be equal to the xp of 0? How long does it take? What has to happen to the product omega times t? If you start off, if it's a cosine, you want to come back to the graph of a cosine looks something like this. How long does it take to come back? Okay, so this is the graph of cosine of x. This is, well, let's call it tau for a minute. This is tau equals 0. When has the cosine got its first 0? Pi over 2. When has it gone back, when has it gone to minus what it started with? Pi. When does it get back to the second 0? 3 pi by 2. And when does it come back to itself? 2 pi, right?
So the period of cosine tau is when tau goes through an interval of 2 pi. If you have cos omega t, how much does t have to go forward in order to get back exactly cos omega t? It would be omega t has to be 2 pi. Okay? Right? Because the cosine of omega t minus phi plus 2 pi is the very same as the cosine of omega t minus phi. So the period of this is 2 pi over omega. So we call t the period. It's the smallest value of t where this function repeats itself. That's the period. This is called the angular frequency. This is called the angular frequency. It's measured in radians per second. Radians per second. But sometimes we like to say just this is 1 over f. This is cycles per second. Omega is 2 pi times f. Okay? The number of radians per second is twice pi the number of cycles per second. What's another name given to a cycle per second? Hertz. So this is hertz. So this is seconds. Hertz has the unit of 1 over seconds. So, for instance, in the LRC circuit, where you're forcing with some radio waves, the frequency, the F frequency, it's roughly a megahertz, a million hertz. A million hertz. That's the frequency. The omega would be 2 pi times that. Okay? That is the frequency, okay, of the excitation. The tuner, the root k over m in the case of the LRC circuit, if you recall, was 1 over the square root of L, the inductance, times C, the capacitance. Okay? When the natural frequency of the circuit, 1 over square root of LC, matches the frequency of the exciting radio wave, omega, then you get the strongest response. You get the highest current response. That's like the highest velocity in this case. That's resonance. Okay? No, omega is the frequency. So it's the frequency you push it with. I mean, for instance, think of the bus stop, right? We push it. What we'll do, our pushes would be like this. Roughly speaking, here's the bus stop. And it's going to go through oscillations. It's going to go 1, and then it's going to come back out this side, and so on. Every time it hits here, every time it gets to the middle, we just give it a push. Just almost like an impulse. So we're going to, the graph of our pushing will look something like this. Nothing, and then we give it a little push. And then nothing, give it a little push. Where this is the natural period. Okay? Now that doesn't quite look like cos omega t, but if you do a little Fourier series, in fact it contains an awful lot of the cos omega t. Alright? So this would be just as good to resonate the circuit with, okay? It's just that when you express this in terms of a sum of cosines, lots of cosines, called a Fourier series, then this has a lot of the cosine of the omega t in it, and enough to do the damage. Sorry?
So what is Z of omega?
Z of omega is, think of what's happened here. In the electrical circuit, when you were on resonance, this would be R. So this would be the resistance of the circuit. But the Z of omega, when you're not on resonance, it contains two terms. The B, the resistance, and this term. So the amount by which you get impeded or damped or thwarted, as it were, is not just due to the resistance, but also due to how much the frequency differs from the natural frequency of the circuit. This has got a name, it's called the reactance. Okay? And so the total resistance, as it were, is the sum, it's the square root of the sum of the squares of the actual resistance and the reactance squared. You had a question now, this gentleman.
Yes. You said that some bridges are destroyed by resonance.
Some bridges destroyed by resonance? Yes, the famous bridge in Seattle. Tacoma Narrows, was it? Yeah. So look it up. Sorry? Yes, I believe that's the...
Actually, that was destroyed by aeroelastic flutter, not resonance.
What's aeroelastic flutter?
It's a phenomenon when air flows parallel to the surface at above a critical velocity, at which the bridge wasn't just moving backwards, cars were up and down. It was actually the cars.
All right. Well, that's another motion, you see. In this complicated mechanical system, it has lots of motions. It has motions like this, okay, and it has motions like twisting, right? I mean, there's many different degrees of freedom in a bridge, okay? So actually what you called the flutter, aeroelastic flutter, was nothing other than a resonance between one of the natural modes of oscillation of the bridge and what wind fluctuations there were from the outside. All right, look it up. All right. Any other questions? Okay, very good. Now, I want to talk a little bit about the so-called complementary function. This is the transient part of the solution. This is the part that eventually will damp away, but it's an oscillation, but it's an oscillation which decays in magnitude due to the factor, the exponential damping term. Okay? Now, I would like to write this in the same way as we wrote this as a root a squared plus b squared cos omega t minus phi. I would like to do the same thing here. Okay, and how do we do it? Now, let me remind you what it is we're after. Now, let me go to this board. All right, so let me remind you now, if we want to write something in the form a cos omega t plus b sine omega t, we would like to write it in the form some constant cos of omega t with a phase lag. What we're going to do is use the idea that cos omega t, cos phi, plus sine omega t, sine phi, is cosine of omega t minus phi. This is the law of cosines. Cosine A minus B is cosine A, cosine B, plus sine A, sine B. But I can't always do that, because in order to identify this with cosine phi and this with sine phi, I must know that the sum of the squares of A and B is equal to 1. Cos squared plus sine squared equals 1. So generally, A and B will not have that property. But I can ensure that they have that property if I divide above and below, or multiply above and below, by the square root of A squared plus B squared. Okay? If I do that, then certainly I can find a phi whose cosine is this and whose sine is this. So I can rewrite this expression then as square root of A squared plus B squared, cosine of omega t minus phi, where cosine phi is A over this square root, and sine phi is B over this square root. Okay. Now, in our example of the complementary function then, the xc of t can be simply written as e to the minus b over 2m t times square root of a squared plus b squared times cosine of root k over m minus b squared over 4m squared t minus phi, where cos phi is this and sine phi is that. Now, is this a periodic function? Is xc, can I add some capital T to little t so that xc of capital T plus little t is equal to xc of little t for all time? Can I do that? What would stop me doing that? Well, it's the fact that you have this decaying term. So if I put little t into t plus big T, there will be a factor of e to the minus b over 2m big T. Yes? No, it'll be, yes, thank you very much. It'll be not the same phi as up there, so thank you. So we will actually put a big C underneath it here. So we'll put a subscript C on it, because it's not the same cosine and sine that appeared in the surviving solution. Okay, nevertheless, even though this isn't periodic, it has repeating structure. For instance, the maxima of this will be 2 pi divided by this frequency apart. The maxima, of course, will decay. They'll get less big as time goes on. But the distance between them in time will indeed be 2 pi over that guy. The distance between zeros of this function will be pi over this distance. So even though it's not periodic, it does have a repeating structure. I'll show you how to write the velocity next day, but that's enough for now. Okay.